It was a long way to get here. I'm very glad to be here. I'm also glad to be out of quarantine and legally vaccinated in 2 countries. Okay, so today we're going to talk about hardware attacks, but we're not going to talk about doing the attack with hardware. We're going to talk about doing the attack with sounds on the radio. We're going to make tricky configurations of radio receivers in order to receive things that we're not supposed to. We're going to make tricky configurations of transmitters in order to transmit raw packets with more detail than we would normally control, so that we can do illegal bits in the header, or so that we can do a shorter preamble than is expected. And we're also going to show how, without having any hardware at all, only by controlling layer 7 data, meaning the pixels of a cat picture or the bytes of an email, we can remotely inject a layer 1 frame from layer 7 data. We'll do this by abusing a packet collision and the fact that when you control unencrypted data on a high-level radio, by flipping bits, you're able to also flip bits within the lowest level layer 1 transmission in order to control how these things sound on the air and might be correctly or incorrectly interpreted by a receiver. If any of you have seen one of these cars, this is called a Studebaker. They're from South Bend, Indiana, and the very last ones were made in Haifa in 1967 and 1968. I'm trying to buy a 67 or 68 in Israel and bring it home to Tennessee. Wish me luck in that. They're really cool cars. This car came with 5 transistors. They're all in the radio that you see in the background, and there were no other transistors anywhere in the car. When you're attacking a hardware implementation like this, you're attacking something that has no computer in it. Or if it has the computer is sort of off on the side and using the radio as a peripheral. So you need to think of it as attacking a state machine rather than attacking anything that runs software. There is no instruction pointer, there is no ALU, there is no CPU in the portion of the radio that is hit by the attacks that we'll cover today. So the first trick is that we're going to take a radio and we're going to reconfigure it to have a different sync field. And then we're going to put a message inside of the body of the packet that we're transmitting with a bad sync field. And this message will become its own layer 1 packet. And this is how we're going to control the header information that would normally be automatically prepended by the radio transmitter chip, so that we can make illegal entries in the field, illegal lengths. This is how you send a packet that is longer than it can be in order to try and overflow a buffer, or how you can shorten the preamble so that you can make a packet that is always received by one brand of receiver chip, but never correctly received by another brand of receiver chip. We're also going to show how to do the same thing in reception. So sometimes you don't know what the synchronization field of a particular packet is, and you need to find it out, but you cannot promiscuously sniff in these types of radios without first configuring the sync field. So what we're going to do is we're going to make a fake sync field, and we're going to disable checksumming, and then we're going to receive background noise as if it were the beginning of a packet, so that the state machine for our receiver will latch on a little bit early and then return the noise that precedes the real packet as if it were a packet with a bad checksum. And this allows us to promiscuously receive on radios that should not support promiscuous reception. The final trick that we're going to show is how to perform the packet-in-packet injection trick. This trick allows you to inject a layer 1 frame only controlling layer 7 data. And in implementation, it's a lot like the first of these 3 tricks, in that we are putting one packet inside of another. The difference is that instead of manually corrupting the outer synchronization field, we're going to let a frame collision in the air do that for us. because frame collisions are very, very common at 2.4 gigahertz. A quick review, and some of this is a little bit higher level than the actual implementation, but most of these details are accurate. A radio packet begins with something called a preamble, and the preamble is a repeating pattern. In a 2FSK chip, this will be 5s or A's. 5, of course, is 0101, and A is 1010. If you have a repeated set of these and you shift them in time, they're the exact same message. The reason for this pattern is that your receiver has its clocks and your transmitter has other clocks, and your receiver needs to correct its own timing in order to know when to sample for a symbol in the transmitter. And the faster your message is, the harder it is to keep these two clocks synchronized. So the purpose of the preamble is to sort of provide some throwaway information for the receiver to read in order to calibrate its amplitude and its timing. And because of that, the preamble is very often optional. And if you leave it off, the packet will still be received, but with more symbol errors. And those symbol errors will become more frequent as your packet becomes longer. Followed by that, you have the first thing that tells the receiver when to begin, like where the packet begins. And this is called the synchronization field or the start of frame delimiter. In Zigbee, this is 00A7. In Shockburst, which is the protocol used by those, well, maybe by this remote here. In those protocols, it's longer, it's 5 bytes long, and it's kind of randomized. It's the serial number of the connection. Because this remote will only connect to its own receiver and it does not need to work with any others. The matching of this is performed by a hardware shift register that shifts the symbols through, and whenever they match this pattern, it latches on, and that is when in time the packet begins. And then the bytes that come after that are the ones that become the header. Usually these fields are left out by your packet sniffer, because your packet sniffer only shows you what the radio forwards upward to the software driver, and it leaves off what the radio crops off. So even though these are transmitted on the air, and even though they have to be there for the receiver to receive the packet, they do not appear in your PCAP file or in Wireshark. Followed by that, you have the fields that you're more familiar with. You have your length, your destination address, you have flags for the features that are enabled, maybe a source address, and then you have your payload, which is controlled by the rest of your stack. And these vary a bit by implementation. So we're going to stick to specific examples wherever possible. And in Zigbee, or IEEE 802.15.4, the preamble is 4 bytes of zeros, and then your synchronization field is 00A7. These 4 bytes of zeros are different from your 5th byte of a zero, in that the 5th 0 byte has to be aligned in time in order to trigger the reception, and the earlier bytes are sometimes optional and are ignored by some implementations of receiver while mandatory by others. If you want to evade a wireless intrusion detection system, you can transmit with fewer of these in order to block out all Texas Instruments chips while allowing Atmel chips to receive the packet. But if you want to experiment with that, the chips have no support for leaving these things off. So maybe you want to transmit a shorter one for fingerprinting, or maybe you want to know if it would work for like saving a power budget. You can use a longer preamble in order to hog the channel to maybe prevent as many packet collisions. And these devices are used in Internet of Things networks, where the peripheral devices are often on battery power, and the access points are very often hardwired to power. So anything that you can do to move the power consumption from an edge device to an access point is good for engineering use. But the experimentation is hard. So the way that you can figure this out The way that you can inject a raw frame is that you can reconfigure the real sync field. This is the 00A7 that marks the start of the packet for the receiver. You can change that to just 00, which is illegal, which means that the receiver will skip right past that point, believing that it's listening to background noise. Then inside of the payload, you can include a full frame, including the synchronization field and the start of frame delimiter. And that is where the receiver will latch in and begin receiving. Here I have 3 packets. The one at the top is a normal standard packet. And in that one, the receiver matches on the 00A7. It then forwards the header and the body up the radio stack to your driver. In the second example, the receiver never recognizes that this first portion, that long string of zeros, it just thinks that's background noise. It skips right over it. It matches on the 00A7 that is later in the frame, and it forwards that body at the very right of the second row up to the networking stack. The third packet does the same trick, except that it has an illegal preamble. It only has 1 byte of zeros instead of 5. And this is an experiment that you can use for fingerprinting. So this lets us inject a custom packet at layer 0 just by virtue of being able to reconfigure the transmitter chip in a sort of standard feature that's designed and exposed by a register. The opposite of this would also be handy. So we've shown how to inject a raw frame, but we would also like to receive a raw frame. And the reason is that there are many wireless keyboards and mice and projector remotes that use the synchronization field as a destination address. On those devices, it's very hard to sniff them promiscuously because you don't quite know where the packet begins, and you don't want to use custom hardware to do it. You would much rather do this as a simple firmware patch. The most direct and most expensive way to receive these packets is by software-defined radio. You can purchase a USRP, you can use a Realtek dongle, but then you're looking at having an entire desktop PC doing the processing in order to get your packets out. Another option, which Max Moser and Torsten Schroeder used in Kikariki version 2, is that you can have a very fast CPU sampling the raw output bit of a rare and strange radio chip from a company called Emicom. And then that can recognize the beginnings of the packets in order to get your addresses out. And then they would forward these to the standard radio chip from Nordic RF. This is a hacker conference badge from the Next Hope, and it is possible to sniff those keyboards in firmware on this badge running from a coin cell by triggering false positive matches on the noise that comes before a packet. So for raw reception, we're going to trigger a false positive match by choosing a starter frame delimiter that is background noise, followed by the very beginning of the legitimate preamble, because we know that the preamble will be transmitted prior to the unknown starter frame marker. Now, we can't just choose the preamble because, first of all, it's repetitive and it has no alignment. The transmitter is going to send many zeros and ones. And if we try to match in the middle of that, we won't quite know where the legitimate address is in the bits that follow. The other problem with it is that it appears in background noise. So very often in background noise, you will hear A's or 5s because that's sort of the sound of the receiver not knowing which bit to sample and then flipping back by a self-oscillation of its clock. So we look at background noise itself, and these A's and these 5s, they're long stretches from self-feedback, and they also look a lot like our preamble, so those are not very useful. But we also have shorter stretches, which are all zeros or all ones. I'm pretty sure that this is what happens when the channel beneath the one that I'm tuned to or just above the one that I'm tuned to, is a little bit active and has more noise than the other side. These are less common, but they are very useful because they're different from the preamble. So if we look for these 00 or FF bytes interrupted by A's or 5s, that should give us the moment in time at which the transmitter begins to override the background noise. And if we can match on that and ignore checksums and forward this up our driver, we will then have the raw beginning of the transmission, including the destination address, the starter frame delimiter that we did not know, and can then program that address back into the standard radio chip in order to catch every keystroke from the keyboard. The other thing that we need to do here is that because we're trying to trigger false positive matches, we need to increase the odds of doing that as much as possible. The Nordic RF chips that are used in these devices have a 5-byte preamble, or sorry, 5-byte sync field that can be reduced down to 3 bytes by the datasheet. And if you play around with values in the register, you can get it even shorter to 2 bytes. And matching on 16 bits is a lot easier than matching on 32 or more bits. So in this uppercase, we have the packet as it is supposed to be received, with Cafe Ba as the synchronization field, and the preamble is 0055. Sorry, it's 5555. Because we don't know that Cafe Ba is the 3-byte destination address, the sync field, we can't simply ask the chip to be promiscuous and receive all packets for us. But what we can do is we can reprogram it in order to have a 2-byte address of 0055, and then we can match at this point so that 55 Cafe Ba and the rest of the legitimate packet get forwarded up the driver to our receiver, so that with checksumming disabled, we can catch those fields within our packet sniffer. We have a couple of other real-world requirements for this. We need to shorten the preamble as much as possible to encourage these false matches. If we kept the original 5 or 3-byte length, we would have to wait much longer for a packet to arrive, because we would need to guess more of the preamble or more of the background noise and be right about that guess. We also need to set a fixed length, because we don't want the garbage that we receive to be interpreted as if it were the length field of the header of the packet. We have to disable checksums, because obviously the checksum will be wrong when you begin reading from the wrong position. And this is lossy and prone to false positives. So we will get both legitimate packets and background noise that happens to match our pattern. We need to filter those out by software. And then as soon as we identify the real sync field, we can plug that back into the receiving address register of the radio, and only then begin to get all of the clear packets with checksum validation, so that we have a clean capture for later. And that's the stage at which you would begin getting all of the keystrokes instead of every 20th. So in our first 2 tricks, we learned how to inject raw packets by changing the sync field to anything wrong. That was our first trick. So we make the sync field wrong, we include a whole layer 1 packet in the body of a transmission, and then the receiver only hears that second valid packet, the one that is inside of the body, because the outer packet with the original sync field that the radio adds as its own header is illegal. It has the wrong sync field, so the receiver never knows that a packet has begun, and it keeps ticking along, believing it's listening to background noise until it finds our interior injected packet. But what if we don't control the synchronization field register of the transmitter? What if we do control data, but we are not able to reconfigure the radio, and we want to inject a raw packet anyways? It turns out that you can do this. And the method for this is called packet in packet. Here at the very beginning, at the top, we have a standard packet as it would be received in IEEE 802.15.4. The preamble, of course, is 4 bytes of zeros in this protocol, and that is background information to synchronize our clock. Then 00A7 is the synchronization field that marks the beginning of the real transmission. And this is what the receiver latches on to know that the packet has begun. It's followed by the header and the body. If we change the 00A7 to 0000, then we break that matching, and the second matching within the outer packet's body occurs. So that the radio receiver thinks that the packet begins over here on the right instead of over on the left where it would naturally begin. This third example, usually it identifies the one on the left, but not always. And the reason why is that there's damage to packets in the air. This is at 2.4 gigahertz, where we have the multiple observer problem. We have the problem that I'm transmitting to all of you. You are different distances from the speakers. You're different distances from my voice. So you hear me with different volumes. If you are having a conversation of your own in this audience, then the person next to you might hear you louder than he hears me, even though for everyone else it sounds good. In radio, the same thing happens. You can never know that the channel is really clear before you transmit. Many transmitters will listen to see that the channel is kind of quiet before transmitting. But when they do, they only hear it from their own position. They don't hear it from the positions of others who might be between them and the other transmitting source. So at 2.4 gigahertz, packets collide and damage each other all the time. So let's look at the damage and what the effects are. If we have a late collision in a packet, then the receiver beginning on the left, it sees the preamble, which is just for timing. Then at 00A7 at the sync field, that's when it latches on. That's when it knows that the packet has begun. And it successfully knows that the packet began. It then sees the header, and it starts reading the body, and the body gets damaged by a colliding Bluetooth packet, a colliding Wi-Fi packet. So in this case, the driver is told first that a packet arrived, and second that the checksum is bad and the packet should be dropped. And if you are sniffing with checksumming disabled, you will see this fragment of a damaged packet. What if the header gets damaged? How is that different? Well, when the header is damaged, you still know that a packet began, but you might not know that the packet was intended for you because you don't have a destination address. And you also don't know the real length of the packet. So in your packet capture, you might have a shorter or a longer record than the real one, including the damage. But you still know that a packet arrived, and you still know that that packet was damaged and that you did not get the whole thing. So you can include this in your error statistics. You can know that the channel is maybe busier or damaged. And what if we move the damage just a little bit earlier? In the real world, this damage would probably also hit the preamble. And this is what would happen if the transmitter thinks that the channel is quiet, and it is from the transmitter's perspective, but from your perspective, you're close to somebody else who is finishing a transmission. So the end of the one transmission damages the beginning of this one. Well, in this case, the sync field is missing. The receiver never hears 00A7, so the receiver never knows that a packet began. And because it never knew that a packet began, you have no record in your PCAP file, and you have no record of a checksum being bad because a packet never happened. So what if we have the same damage in our third case from earlier with a valid packet in the body and the original start of frame delimiter damaged by a frame collision? Well, in this case, the receiving radio skips over the initial 00A7. It does not know that the frame actually began. So it keeps running. It keeps looking at the next symbol and the next symbol hoping that a packet will begin because that's a radio's job during background noise. And then it sees this real preamble, all these nice little zeros to get the timing right. And then it sees a 00A7. And it latches in. The state machine says, all right, we've got a packet. It then begins ticking off the header of that packet, the body of that packet, all the different pieces of it. It loads it into a buffer, it runs the checksum, and the checksum is right. So it then forwards that up the networking stack. And from the networking driver's perspective, this interior packet is real. It has a valid header, it has a valid checksum. There is no way, there's no possible way for it to know that this is inside of the outer packet because of the accidental damage of the frame collision. And this does not show up as a bad checksum in your packet capture. This shows up as a good checksum. And if you're running a real networking stack, it gets forwarded up the stack. And you have remotely injected a layer 1 frame controlling only layer 7 data. There are a few complications from this. The first is that you have to know what your symbols will sound like on the air in order to do this attack. So in the case of Zigbee, the case that we covered before, whatever byte you have in your data also becomes a byte on the air. Wi-Fi is not like that. In 802.11b, you have two complications. The first is that there is a scrambler. So in 802.11b, there is 127 state, 7-bit scrambler that is self-synchronizing between the transmitter and the receiver. And in order to perform a packet-in-packet attack against Wi-Fi, you need not only a frame collision to damage the original header, but you also need to correct for the scrambler. And then that was 11b, that was 15, 20 years ago. With modern Wi-Fi, you also have encryption. If the packet is encrypted and I don't know both the key and the nonce and any other fields that might complicate it, then I don't know how to make the symbols on the air match what I want them to form a valid packet. This also requires frame collisions, which at 2.4 gigahertz are very, very common. Wi-Fi has the strategy that it reserves the channel. So a Wi-Fi packet is preceded by a header that says, hey, everybody, I'm making a transmission that will last 100 milliseconds. I need all of you to stay off of the channel and leave me be. Bluetooth uses the opposite strategy. Bluetooth just transmits whatever the hell it wants, colliding with Wi-Fi or other Bluetooth. And if a frame gets lost, tough shit, that's the world, keeps on going, jumps to another channel and tries again. And either of these individually is a very good strategy. But when you combine the two, then the Wi-Fi can't know that the Bluetooth is going to be in the way, and the Bluetooth can't know that the Wi-Fi is going to be in the way. And then you take all of us who are in the room, and we each have a cell phone, and the cell phone is on 2.4 gig as well. And half of them are connected to the Wi-Fi, and half of them are searching for their home Wi-Fi. All of this noise creates a ton of frame collisions that allow for packet-in-packet to happen in short order. In our experiments with Zigbee, we were able to get packets to begin appearing within minutes. And by moving the transmitter and the receiver the right distance away, we were able to get repeated injections every second or so. Ethernet and fiber have a very different situation because they don't have a common medium. And in those systems, the core of the packet-in-packet effect, that the interior can be mistaken for a full packet, that is still there. That Andrea Barasani and a few other clever folks have demonstrated that on Ethernet. But because there are no frame collisions, you need something else to obscure the start of the packet. You need something to replace that frame collision damage. One option might be resetting a shared medium switch, like having a power cycle of a hub. Another example might be just having an interfering signal at the right moment. You know, the fiber gets bent and damage happens. There are other protocols with complications that use spreading codes. So like you have this 810 code within the early versions of PCI Express. It's more complicated in more recent versions. And this means that to have a full byte on the wire, you need to send 10 bits instead of 8. And if any of those are damaged, you wind up in an illegal state or in a state that means something else. And the ones that mean something else are the ones that are used to mark the start and the end of a transmission. So they're not something that you're able to directly create within your message. But with new tricks, who knows? That's what I've got for you today. I hope that you had fun and that you realized that the radio chips and the state machines that power them can be attacked in ways that allow us to remotely sniff and inject using commodity equipment with prices on the order of 10 or 20 shekels, rather than requiring the thousands of dollar laboratory equipment that you might use for fancier stuff. And also that there are new tricks to be found here, that not all of the problems and solutions have been discovered yet. It'll be great for future research topics as more people dive into it and begin to see how these machines misbehave. If you'd like to grab a screenshot or a quick camera shot of this slide, these will be the papers to chase down elsewhere. You can also just pick one of the recent ones and chase its references. Maybe Paco GTFO 3.5 or Woot from 2016. Thank you kindly.